Please tell me when, Sophia.
There's a whole bunch of people upstairs who are still guzzling
Okay. Oh, there we go, there we go.
Oh, nice.
Thanks for coming.
Well, it's online, so a lot of people, it's just hard to mobilize people in person these days, right? Especially this time, holidays now.
Oh, exactly. Hello, hello, welcome. Yeah.
Very cozy.
Very much so, yeah.
Good evening and welcome. For those of you who don't know me, my name is Yasemin Didem Aktaş and I am the chair of the EEFIT Management Committee. We are here today for a very exciting lecture for EEFIT that is titled The Seismic Design for Functional Recovery Performance. That's going to be delivered by Carlos Molina Hutt. I guess most of us are familiar with EEFIT and what it stands for, but I'm going to take this opportunity to tell you a little bit more about it, just in case there are those who are not familiar with EEFIT. EEFIT is a specialist group that operates under ISTRAC-T since 1980s. What we do is we carry out detailed technical evaluations of the performance of structures, foundations, civil engineering works, and industrial plants within the earthquake hit areas. We do collect geological seismographic data and assess the effectiveness of repair and retrofit in the earthquake hit areas. For the past quite some time now, we have increased our scope and remit to also incorporate the disaster management procedures study and an investigation of the socioeconomic effects of earthquakes. And we do all of this by mission work, of course, above all. We do organize training courses and we work with disaster management stakeholders worldwide to be able to make the most out of our work and really be influential on the disaster resilience worldwide. You are seeing a few of our most recent activities. The latest report that we have published is a 2025 Myanmar earthquake report that you can find on our website. And we are currently working with on a report that focuses on the Afghanistan earthquake 2025, August 2025 events in collaboration with our French colleagues and Pakistani colleagues. And please stay tuned for this report, which we're going to release very, very soon. As part of my role, I also need to read this out loud. To the institution's best knowledge, copyright permission has been provided for all material shown, and this broadcast is therefore presented in all good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed, or by agreement, an appropriate acknowledgement provided to accompany the recording post-event. With this, I am very happy to give you Carlos Molina Hutt, who, apart from being an old colleague and a dear friend, is an associate professor of structural and earthquake engineering at the University of British Columbia in Vancouver, Canada, where he leads the Engineering for Seismic Resilience Research Lab. Without further ado, Carlos, please come and join us. Thank you.
Okay. Thank you very much, Jasmine, for the introduction, and all of you who are here in person, thank you for joining, and for those who are online. So as you heard, my name is Carlos Molina Hutt, and I'm an associate professor of structural and earthquake engineering at the University of British Columbia, or UBC. And I'm also a member of this Functional Recovery Task Committee, which was put together by the U.S. Building Seismic Safety Council, and charged with developing prescriptive design provisions for functional recovery performance that we can use in the next generation of our building codes and standards, at least in the US. So the goal of this presentation really is to share with you the research that's underpinning these new provisions that are going to be published next year under the 2026 NEHRB recommended provisions, which, as I'll explain later, those are essentially the starting point for any updates that go into ASC 7, which then make their way into the International Building Code. So that's sort of the goal for today's session. But before getting started, I did want to take this opportunity to introduce my research group. So I'm grateful that Jasmine mentioned that. So I lead the Engineering for Seismic Resilience Laboratory, or ESR Lab, at UBC. We have our website linked down here. Our work primarily focuses on quantifying seismic risk in buildings and infrastructure and its implications on urban resilience. And we try to develop tools and data that are useful to structural engineers, but also seismic planners and policymakers. And I think the work that I'll be showing today, has a very clear link to the building code, but we also do other types of projects where we focus more on like regional scale type of assessments, working with municipalities, province level, and so on. So this is the composition of my group currently. I have a postdoc, 4 PhD students, our little helper, Whiskey. And to the right here, I have a former student, Kristen Blows, who just graduated a few months ago. And I just want to acknowledge that she's done a lot of the work that I'll be sharing with you today. She's now a postdoc at the University of Colorado Boulder with Abby Lyle, that some of you may know. Okay, so the last thing before I actually get started with the technical presentation, this disclaimer that the 2026 NEHR provisions haven't been published yet, and we go through a pretty thorough, consensus-based process where there's a lot of committees, a lot of voting, a lot of addressing comments, and so on. So this is just to say that the final result is not published yet. So when you do go look at the provisions in 2026, there might be some differences between what I'm presenting today and what you'll see in that final deliverable. So there's going to be a little footnote, in all of my slides moving forward that just, reminds you of that in case you take a snapshot or use, the recording later on and things are different from the provisions. This is the last edition of the provisions, which was published in 2020. Okay, so with that now, I can get into the technical content of the presentation. I've divided it in 3 parts. So the first part, I'm going to set the foundation for functional recovery. And what I mean by that is I'm going to talk about the need for functional recovery design, the research foundation that has enabled us to really think about bringing this into the building code. I'll define what I mean by functional recovery because it's something that's fairly new and it might mean different things to different people, and then I'll introduce categories and ground motion considerations that we're using in these prescriptive design requirements. And then the second and third part are going to focus on our approach to develop provisions for structural systems, and then our approach to develop provisions for non-structural systems. And these parts are going to be similar in the sense that the structure will be almost identical. I'll start by talking a little bit about the scope of the work that we carried out, then the methodology, and then I'll use an example, through section 2 and 3 so that you understand what it is that we did to really kind of bring all of this together. So let's start with setting the stage. Why do we even need functional recovery design? And depending on who you ask, some people say that this is not necessarily a need or a priority. I don't necessarily feel that way, and let me tell you why. So modern seismic design codes intend to ensure life safety in extreme events, but they don't necessarily limit damage that hinders functionality or other recovery states. And at least in the US, policymakers have recognized that we really need to go beyond life safety and start thinking about functional recovery. And as a result, we've seen bills in the US Senate, for instance, dating back to 2018, or the California Legislative Assembly in 2021 that called for the performance of buildings to be expressed in terms of reoccupancy and functional recovery time, right? So this was essentially a mandate. I also like thinking of past earthquake events. Some of you may recognize these photos. I don't know, does anyone recognize where these photos?
Mexico?
It's Christchurch, New Zealand. But yeah, dating back a few more years. But good guesses. So this is a view of downtown Christchurch, literally seconds after the earthquake, right? So you can sort of see the cloud of dust and a lot of the debris after that event. And I like thinking of this or using this example to make my point, because if you think about this particular event or this earthquake sequence, I believe around 180 people died, sadly, after that event, primarily because of the collapse of 2 buildings. However, there were 600 buildings that were demolished, and the central business district was closed off for 2 years after the event. So despite those staggering statistics, if you ask engineers about the performance of buildings, they would argue that for the most part, they did as they were intended to, right? They followed what the code wanted them to do, which is to meet, life safety goals, again, with a few exceptions. And I think this really emphasizes the need that if we want our communities to truly be resilient, we need to do more than just design for life safety, and hence this push for functional recovery. I also want to reflect on past work that has allowed us to now, try to codify functional recovery. And I obviously need to mention the FEMA P58 project that some of you may recognize. This was originally published in 2012, and at the time it was the next generation of performance-based seismic design guidelines that really allow you to describe building performance using metrics that were a little bit easier to communicate, like damage, repair cost, or repair time. And building on this framework, there have since been a number of studies that have proposed, frameworks that build on these metrics to really evaluate recovery time, which is a little bit more than what was done by FEMA P58. And some of you may recognize the Arab Ready guidelines. I would argue these were pretty pioneering at the time. They were published in 2013, so right after FEMA P58. However, they didn't necessarily have code associated with it, right? It was more of like a methodology on paper, so a little bit hard to then translate that to projects. And more recently, there have been a number of studies, like my students and I published this framework called TREADS, or Tool for Recovery Estimation and Downtime Simulation of Buildings, and there's a paper associated with that and code available online. Vesna Tursik and her students published this framework called EFREC, and Dustin Cook, Abilal, and others published another framework that was recently adopted by this new project, ATC 138, that will also be released very, very soon, that essentially takes FEMA P58 and extends it to do assessments of functional recovery time. And that is what we used in this work to develop these new provisions for functional recovery performance. So what do I mean when I say functional recovery? So this is a definition that we plan to include in the provisions. Functional recovery is the post-earthquake recovery state in which a structure is maintained or restored to support the basic intended functions associated with its pre-event use or occupancy. And I think it's pretty important to emphasize that, a functional recovery objective doesn't necessarily mean everything needs to be back up and running immediately after the earthquake. It recognizes there are different types of buildings that offer services that might be needed at different times, right? So there's a time component to this. It doesn't necessarily mean everything must work on day zero, right? Because that would be very costly, and we would be designing all of our buildings to maybe criteria that's unnecessary and maybe too conservative. I have a little cartoon here to the right that kind of describes what happens after an earthquake if a building experiences damage, and it's recognizing the fact that there might be a series of impeding factors, things that need to be addressed before we can do repairs, like the post-earthquake inspection of the building, mobilizing an engineer or a contractor to do redesign work, retrofit work, and then carry out the repair activities, financing, permitting, so on, things that are very real, right, and take time, and you need to address before you can start doing repair work to then reach different recovery states. And I also like this diagram because it showcases that functional recovery is less than full recovery. It's not like everything has gone exactly back to normal, but it's more than the minimum that would be expected for a building to be occupiable after an earthquake. There's also this nice cartoon, which I think is a lot better than the one I had in the previous slide. It was recently published by NIST, and it does a really good job at trying to convey the differences between life safety design in the bottom and functional recovery design in the top, right? So in the bottom, we can see that, after an earthquake, a building could experience moderate or even significant damage, and it will essentially be out of commission until you've conducted all the necessary repairs, right? And can use it again. Whereas the goal with functional recovery is that we're going to minimize that damage so that we can, within a reasonable time frame, ensure that the basic intended functions of the building are up and running again, and this would happen before full recovery. And I have a link to this graphic if you're curious to look over it in more detail. Okay, so in the context of this work and this new chapter, or it's actually going to be in the form of an appendix to the NEHR provisions, when you're designing a building for functional recovery, you're going to essentially associate it or flag it with a particular functional recovery category. And the functional recovery category is going to depend on the types of services that those buildings provide to the community. And there's going to be a recovery time target associated with each one of those. So for functional recovery A, this would be the most important type of building. We're targeting effectively immediate recovery, so 0 hours of recovery. B, recovery within 3 days, so a little bit more relaxed than A, but also critical services. C, now we're talking about 2 months, and D, 6 months. And this may seem very similar to what we're already doing in the US, which is assigning risk categories to buildings when we design them. Some of you may be familiar with a risk category 4, which is a hospital building, essentially, that type of facility. But the mapping is not one-to-one. And the example that I like to use is housing. So housing or residential occupancies in the US, if you're doing a life safety design, it's a risk category 2. That's like a normal importance building. And in functional recovery, we're actually putting housing under functional recovery category B, which would mean you want, that housing to effectively be able to provide people shelter, right? To provide its basic intended function within 3 days. And that's sort of recognizing that if people can't go back to their homes, you're not really empowering or enabling a fast recovery of the community. So this is a pretty important mapping exercise that took place at the beginning of this process and was led by some colleagues that I'll acknowledge later, but pretty important to go through this exercise and recognize that different buildings have different recovery time targets. Now, when it comes to the ground motion characterization that we're using in our design, we're effectively replicating the process that is done in the US to design for life safety. In the US, unlike in other geographic locations throughout the world, they don't design for a particular hazard level, meaning they don't choose to design for a 2,500-year event or a 500-year event. They use this risk-targeted approach, which integrates the full hazard curve when they're determining their design ground motions. So this risk-targeted approach implies or requires having a risk target, which kind of looks at the lifespan of the structure, and a reliability target, which is sort of conditioned on the shaking intensity at which you're doing your design. So for life safety, and some of these metrics may sound familiar to you, we're targeting a 1% chance of collapse in 50 years, or a 10% chance of collapse conditioned on the risk-targeted maximum considered earthquake ground motions. Following the structure for functional recovery, our risk target is to have a 10% chance of exceeding that recovery time target in 50 years, and a reliability target, which is a bit more relaxed, right, from collapse, just as a risk target is, just because the implications of function are a lot less severe than the implications of collapse. We have a 25% chance of exceeding that recovery time target that I previously introduced. And you have a little bit of a table here summarizing these metrics. What I think is most important to recognize that what we're designing for, which is the functional recovery earthquake, is less than what we typically use to design for life safety, right? So we're looking at generally lower return periods. And if you prefer to look at this in a more graphical way, I have a couple figures here. The one on the left is giving you the relationship between the 1 second design spectral acceleration for functional recovery in relation to the 1 second design spectral acceleration for life safety. And everything you can see falls below the 1-to-1 line. The different colors here denote different regions within the US. And the figure on the right is giving you a sense of what the return period is for the functional recovery earthquake. As I mentioned, in the US, they use this risk-based or risk-targeted approach. So the return period that you use in design is different wherever you are, right? And this kind of gives you that sense. The colors, again, denote different regions in the US. But what you can see is that the functional recovery earthquake, typically for most sites, is within the 350 to 400 years. So lower than what we do for life safety design. So the way we went about developing prescriptive provisions that could be applied throughout was by making use of this DMAX FRE spectrum. This is analogous to what is done in the FEMA P695 methodology. They have a DMAX spectrum. And this document, or this method, essentially is the method that's used in the US to come up with R values, or response modification coefficients, for different structural systems. So we're kind of replicating this process, but for functional recovery, right, as opposed to for life safety. So we're using this concept of Dmax, but now applying it to the functional recovery earthquake. And the way I like to think about it is essentially, a sort of enveloping spectrum. In more concise words, it's a single spectrum that's representative of the most critical conditions, right, that a building would experience if it's being designed using prescriptive requirements. So it's not all comprehensive. It has some limitations when it comes to like soft soils and things of that nature, but it's a good way to develop these prescriptive requirements. And the plot on the right gives you a sense of how the Dmax FRE is in relation to the Dmax. DE is the design earthquake, which in the US is 2/3 of the maximum considered earthquake, and that's what we use in design. And the ratios vary, but it's the functional recovery earthquake spectrum is roughly 75 to 80% of what we use in relation to collapse. Okay, so with the definition in mind, with the notion of these functional recovery categories, and a sense of the ground motion hazard that we're using in our designs, now I want to tell you a little bit about our approach to developing design requirements for structural systems. And I want to start by just showing some of the systems that we've initially considered in this process. So you can see in this table that we have a range of reinforced concrete shear wall systems. So we have cantilevered and coupled walls, shear governed, flexure governed, also bearing wall versus building frame systems. We also have a couple of steel brace frame systems here, in particular focusing on buckling restraint brace frames with and without moment connections, and also moment frames, looking at steel and concrete. And initially we've been looking at these systems that are already available in ASC 7 Chapter 12 when you're doing a life safety design, and looking at a broad range of heights and different gravity systems also that are combined typically with these lateral systems. And I'll talk a little bit more about that in the coming slides. You might be wondering, why are you looking at conventional systems, right? If you want to design for functional recovery today, you're probably using innovative approaches like base isolation, supplemental damping devices, and things of that nature. And we recognize that is, a probably better way to go about it, but that's already being done. And our goal here is to make functional recovery accessible, because the vast majority of our buildings are designed following prescriptive requirements, like, an R factor, a drift limit, and so on, and they're conventional systems. And what we want to do is make this design process accessible, right? So it's not only your base isolated buildings or your buildings with supplemental damping devices that can achieve functional recovery. So that's the goal there. And I have highlighted here special reinforced concrete moment frames, because that's the example that I'll use later on to kind of walk you through what we've been doing. Okay, so what are key considerations when it comes to the design of structural systems? So the most noteworthy ones are the fact that the lateral force resisting system is going to be designed to have reduced ductility demands, right? We recognize that ductility is essentially damage. So we're going to try to reduce those demands using an RFR. This is a response modification coefficient that's going to be effectively lower than what we use in life safety design. So that's the first thing. This would be similar to the Q, or behavior factor, in the Eurocode. And then the other one is that we're introducing allowable story drift limits that are going to go anywhere from 0.75% to 1.5%. And there are a couple things here. These values are going to depend on the functional recovery category, because we have different targets, but they're also going to be system specific. And while currently for life safety design our values are system specific, we typically have a drift limit that applies across the board, right? And what we're doing differently here is we're recognizing that for functional recovery design, different systems are going to have their own drift limits, right? Because the amount of damage that a system will experience when it is pushed to a certain drift level can vary significantly. So that's sort of what we're recognizing. And this is a snapshot of the types of results that we'll be reporting for different systems and different functional recovery categories. We're going to have this RFR, or response modification factor, for functional recovery, a drift limit, and an RMUFR, which is more related to non-structural system design. So I'll circle back on this variable later on. Okay, so in essence, to come up with RFR and drift limits for functional recovery design for this range of systems, we're effectively looking only at a subset, as I showed in the previous slide, and thinking both of the lateral system in combination with a gravity system, right? Because damage to the gravity system can equally lead to essentially a lengthy recovery time. We're looking at a range of heights, anywhere from 3 to 24 stories, and we're evaluating the performance of this, broad range of systems and archetypes, looking at different possible combinations of this RFR and drift limit. So we're creating a design space where our RFR values are going to go anywhere from 1, which is an elastic design, to the R that we currently use in life safety, which also varies from system to system. And then in terms of drift limits, we're exploring anywhere from 0.5% to 2%. And all of this is conditioned on the new functional recovery earthquake. So you might be wondering, well, what are you measuring in this design space? And our performance metric is what we're calling safety critical structural damage, which is essentially damage that must be repaired before a building can be occupied safely. And the key idea here is that, if you experience safety critical structural damage, you're going to have a very lengthy recovery time. So we want to try to minimize this, and by exploring this design space, we can then select values of RFR and delta AFR or drift limit that minimize this probability of safety critical structural damage. So I want to tell you a little bit more about this metric so you understand how we're going about actually calculating it. So safety critical structural damage is effectively going to aggregate damage to different components in your structure all the way to a building level metric that we can use to make decisions. And it's going to capture whether there's been substantial loss of lateral and or vertical load carrying capacity in the different components of the structure. So it's really trying to think about how severe the damage is and how much of that damage there is and how it is distributed throughout the structure. So to do that, we're using this fault tree that you can see on the right, and there are 3 key branches. And I'm going to focus initially on the one on the left. So essentially what we're doing is we're looking at every story in the building and every building direction and evaluating the amount of components that have experienced different levels of damage. And we're describing this in terms of what we call a safety class. So there needs to be a mapping of damage states in different components to safety classes. For instance, a safety class of 1 would be a description of damage to a component that might be moderate and potentially even visually concerning, but actually it doesn't lead to strength loss. A safety class of 2 would be severe damage that does lead to lateral strength loss in the component, and a safety class of 3 would imply both lateral and vertical load carrying capacity. So of course, the more severe the damage or the higher the safety class, then there's a lower percentage of components that we can tolerate in that safety class before we deem, that story and therefore that building as experiencing safety critical structural damage. So that's a little bit of the thinking. Of course, if you had excessive residual drifts or collapse, that would also mean safety critical structural damage. But in the context of these provisions, we're looking at buildings that at minimum are designed for life safety. So we're already, essentially tackling this one here. And residual drift, could have a prominent role in some systems over others, but it's something that we're also considering, because if you had excessive permanent deformations, essentially that's also safety critical structural damage. And one quick note here, my last point is to recognize that we're calling this safety critical structural damage, and maybe as I'm describing it, you're thinking that this is equivalent to an unsafe placard, and it has a lot of parallels, right? But we didn't want to use that term because in our analysis, we're only looking at damage to the structure. Whereas in reality, if you go out to the field after an earthquake and you're doing post-earthquake safety evaluations, before giving a building a red, a yellow, or a green tag, you're thinking about more than the structure, right? You might recognize that maybe there's non-structural damage in the facade, falling hazards, gas leaks, other conditions that lead to a red tag that aren't necessarily the structure. So that's why we have a slightly different term to recognize that we're not trying to necessarily only replicate the decision of a field evaluator after an earthquake. So how did we go about this process? So there are a number of steps. The first one is to define model parameters. We did this for many systems, right? So this means we need to choose the lateral system that we're looking into, the associated gravity system. We need to pick the number of stories that we're exploring, the floor plan, the configuration, right, of that particular archetype. We're going to then develop a series of simplified MDOF models. And what we're doing here is try to create this design space that I was alluding to. So essentially, we're using the simplified approach to be able to create a space where we can easily define, lots of possible archetypes that represent different values of RFR, again, going from 1 to R, and drift limits from 0.5 to 2%. And to do this, we're making use of the seismic response prediction program that's available through SP3 to really automate a lot of this process. Once we've created this design space, we then evaluate nonlinear response to understand how that particular design is going to respond under the functional recovery earthquake. And we're taking those engineering demand parameters and feeding them into a FEMA P58 assessment, where initially we're only looking at damage to the structure, lateral and gravity system. And using those damage state estimates, we then go through that fault tree that I previously introduced to evaluate whether there's this probability of safety critical structural damage. So there's a lot to unpack there, and obviously I went through it pretty quickly, but I have a link at the end to a study that was just accepted for publication in Earthquake Spectra that goes over all the details. So if you're interested in reading more, I'll refer you to that paper. So let's try to illustrate this looking at one example. So I mentioned I'm going to use a reinforced concrete moment frame for illustration. These are the results for a single height, right? We also looked at a range of height. So this is an 8-story special reinforced concrete moment frame. And because of the design space that we're exploring, right, where we have drift limits from 0.5% to 2% and RFR values from 1 to R, which is an R of 8, it's what we use in life safety design, we have 56 design variations of this one archetype. And what you can see here is the realized drift, right, of these different designs. And as you'd expect, the tighter the drift limit, the lower the realized drift. And by contrast, the tighter the drift limit, the stiffer the structure, the higher the accelerations that you're going to experience. And this doesn't matter so much when we're talking about the structure, but because we're talking about functional recovery, non-structural components are very important. And that's why we need to circle back later and make sure that we're accounting for, the large accelerations associated with potentially very, very stiff structures. You can look at the same relationship in terms of the RFR, right? So these are the same results, just expressed in a slightly different way. And same thing, right? For RFRs that are lower, essentially more elastic designs, you have lower drifts, but by contrast, you have larger accelerations, as you would expect. Okay, so those engineering demand parameters are then fed into this FEMA P58 model, right? Where we're trying to evaluate damage to different structural components. So this is a list of the structural components that we would have in this 8-story reinforced concrete moment frame. Primarily, we would have beam column subassemblies of the moment frame, whether they have one or two beams framing into it. And then we also have components that are representative of the gravity system. In this case, we're looking at post-tension concrete flat slabs. So what I want to recognize here is that there are different damage states for these components, right? And we have fragility data for each one of them. But what's important is the mapping to this SC or safety class, right? Which is what we need for the analysis of that fault tree that I previously introduced. And of course, when making this decision, you want just more than those variables. You want to make sure that for each one of these damage states, you have a detailed description of the damage, right? That's described in that fragility function, because that's what you're going to use to do that mapping exercise from a damage state descriptor and an associated repair to a safety class, which is what will really influence the outcomes of this analysis. Okay, so for this 1-story or 8-story reinforced concrete moment frame, right, and all of its 56 possible design variations, how did we make decisions? How did we interpret the results? Well, we created these contour plots, which we thought were a really good way to inform decision making for these provisions, and this is why. So what we have in these contours in the x-axis is the range of RFR values that we explored from an elastic design to the R that we use in life safety. And then in the y-axis, we have the drift limits considered, right? From 0.5% to 2%. So each one of the dots that you see here is a description of the probability of safety critical structural damage conditioned on this, Dmax FRE spectrum. And then we have the contours that kind of delineate, right, where you fall depending on your choice of RFR and drift limit. And what you see is that if you use values that are consistent with life safety, which would be an R of 8 and a 2% drift limit, you're going to have very high probabilities of safety critical structural damage. And that's expected because if we're doing life safety design, we're not necessarily designing for repairability. You know, as I reflect back on those statistics that I shared earlier from Christchurch, right? We had 600 buildings that had to be demolished. So this is no surprise. But what we can see on a more positive note is that if we adopt lower values of RFR and lower drift limits, then we can really minimize the probability of safety critical structural damage. And this is how we selected parameters to introduce into the standard. And we typically targeted having a 10% or less probability of safety critical structural damage to then make it into that table that I was showing earlier. And of course, we had to consider how that applied to the different heights that we're exploring and the different configurations for any given system, because these are going to be system specific. Another interesting thing that came out of this exercise is that you can start to tease out whether certain designs are going to be, you know, strength controlled or drift controlled. So for instance, if you look at moderate to high values of RFR, these lines become sort of horizontal. So it essentially gives you a sense that, you know, they don't vary with R, and that's because they're controlled by drift. By contrast, if you look at very low values of RFR, these lines are vertical, and that gives you a sense that, you know, they're effectively not varying with drift because they're controlled by strength, right? They're controlled by the low values of R, which impose significantly high strength in those designs. So also, you know, useful info that you can tease out from these figures. What we also did is look at the results in the format of these figures here, where we look at the relationship between the realized drift in the x-axis and the probability of safety critical structural damage in the y. The figures are the same. One is just expressing results in terms of drift limit on the left and in terms of RFR on the right. And this really pushed us to specify system-specific drift limits, because we realized that it is a lot easier to minimize the probability of safety critical damage by controlling with drift as opposed to just controlling with strength. You can get there with strength, but the relationship is less clear, right, between those two, and that's why we did something that's different from life safety design. So as you'd expect, you know, I showed a table with a lot of systems earlier. We did this, you know, for any one system. We picked a range of gravity systems that could go with it. We looked at a range of heights, and then we repeated this for other systems that I included in the table. And you can see that these contour plots can vary a lot, right, from system to system. But hopefully this gives you a sense of how we could then select appropriate combinations of RFR and drift limit to give us low probabilities of safety critical structural damage. And that's kind of how we went about this exercise. And this is the result after all that work. Really what goes into the table is something like this, right? These three parameters that I previously introduced, we'll go back to the R mu there later when we talk about non-structural component design, but in essence an RFR and a drift limit that's different for different functional recovery categories for the systems that are listed, and then highlighted again the example that we chose. Now, I mentioned, you know, we go through a very strict consensus-based process to really get these provisions approved. And what the provisions update committee was really keen to see, in addition to these analyses, which they appreciate, but, you know, some people are skeptical and with reason of something that's this new. So they wanted to introduce judgment-based filters. So they essentially said, well, in addition to your analysis, we believe that you should introduce limits that are consistent with what we do now for a risk category 4 structure, which is a hospital building. And that would be using R over 1.5 and a 1% drift limit. So the idea here, at least for functional recovery categories A, B, and C, is that, you know, we looked at the value from our analysis, we compared it to these judgment-based limits, and then, you know, we took the most onerous of the two. And we have a similar approach for functional recovery category D, but everything is a little bit more relaxed because, you know, recovery category D has 6 months of recovery target, so it's pretty distinct from A, B, and C. Okay, I'm now going to transition to the non-structural system design approach, and I have the same table that I had in the previous slide, and that's by design, because the point of departure for non-structural system design is effectively having structural system design that minimizes the probability of safety critical structural damage. So what we did after coming up with these recommendations for structural systems, is say, okay, you need to first meet this design for the structure. It means you're going to have a low probability of the safety critical damage, and only then can we think about the non-structural components. So that's why I'm kind of repeating the table here. What are key elements that you're going to find in these provisions when it comes to non-structural system design? The first one is that we're introducing this seismic floor acceleration demand, and we're deriving this using FPFR. FPFR is similar to what you find in AEC 7 Chapter 13, which relates to the design of non-structural components, and it gives you an estimate of the force, right, that component needs to be designed for. So from that equation, adjusted for functional recovery terms, we then derive this floor acceleration demand. And the idea is, if you're designing for functional recovery, you need to make sure your non-structural components, both drift and acceleration sensitive, can withstand these demands. So that's the first thing. We also introduce the seismic functional recovery component importance factor, which is going to vary depending on the functional recovery category. And this is essentially going to amplify the design forces in your non-structural components. It also affects drift sensitive components because it amplifies the seismic relative displacements that you need to accommodate. And by doing this, you're effectively minimizing the probability that damage in these components could lead to loss of function. And all of this, may sound very, very stringent and potentially well above what we do currently for life safety design. And that's why we introduce a series of floor acceleration thresholds. And we say, okay, if your accelerations are below these levels, you don't need to worry about qualifying your equipment and designing all the non-structural components for these forces to ensure that, we're not passing or introducing something that is just, not economically feasible. So that's kind of in a nutshell what you'll find on the non-structural side in these new provisions. So the RMUFR I mentioned earlier, what it does in this equation here is it reduces the potential forces that non-structural components need to be designed for in recognition of the ductility in the structural system, right? So that is structural system specific, and that's why we need to specify an RMUFR when we're specifying the seismic force resisting system, and that's why we had that variable also in the previous section reported. Okay, how did we go about developing these provisions for non-structural system design? This framework may look pretty similar to the one that I introduced a few slides back for structural systems, but it has subtle differences. And the first ones is that, in step 1 and step 2, actually even in step 3, we're not exploring that design space that I was looking at earlier, right? With a broad range of R's and drift limits, we're saying you're using systems that are designed to have very low probabilities of safety critical structural damage, right? So we're not iterating in that regard. We've already done that as part of the structural system design. What we're also doing differently is that now in step 4, we're not just looking at structural components, we're introducing non-structural components. And this is where the variations or the exploration comes into play. What we wanted to do is understand, how these buildings perform if you introduce the seismic qualification of equipment, if you require that, right, for the FPFR levels that I introduced, or what happens if we vary IPFR. And in this case, we explored values from 1 to 3 to understand how that would minimize the probability of extensive, recovery times. And what's also different in step 5 is that we're no longer just looking at safety critical damage. We're now explicitly evaluating recovery time using this ATC 138 framework that I previously introduced. You might be wondering how we determine whether non-structural systems are functional or not. So I just wanted to quickly showcase another fault tree similar to the one that I showed earlier for the structural system to give you a sense of how this works, right? So for different structural and non-structural systems, we're going to have diagrams like this one that relate component level damage to system level functionality at the top. And as you might recall from the structural exercise, in essence, for each one of these components, what I've color-coded on the sides are different fragility functions, be it for equipment or for anchorage of the component, that can help you understand whether there's been damage in the component that leads to loss of function and ultimately would lead to loss of functionality in the system, not just the component. So in this part of the process, in essence, what we're really doing is verifying whether the designs that we're proposing meet those recovery goals that I introduced at the beginning. And we're doing that by looking at all the variables, right? RFR and delta AFR to limit safety critical damage, and now IPFR and qualification to limit non-structural component damage. So we're actually explicitly checking by using this methodology whether we're meeting that reliability target, right, of 25% probability of exceeding the different recovery times associated with each recovery category. And I mentioned earlier, we attributed 10% to the structure when we were looking at safety critical damage, so that's already captured, and that kind of means that you have up to 15% probability of damage in non-structural components as like your wiggle room, right, to be below that 25% target. So the way we went about this exercise to determine whether we needed qualification of equipment and what would be an appropriate value of IPFR is by summarizing our analysis in this fashion. So this is a very simple figure, but it was very useful to us to then determine what values of IPFR to use. And again, these are figures for one building, right? So it's still the 8-story reinforced concrete moment frame with PT slabs evaluated at that Dmax spectrum. So what we have are, the RFR factors and delta AFR associated with the different recovery categories. So we've assigned to those, and now we're seeing how we perform building level with non-structural components, right? In different ways. So what we have in the figure on the left is a series of results if you don't qualify equipment to those forces that are associated with FPFR, and in the right if you do. What are these figures telling you? They're telling you the probability that the functional recovery time in your design exceeds the target. That means that anything above this dashed line is above the target, no good, right? We need to be below it. So very quickly you identify that if you want to meet your targets, you're going to have to qualify equipment. So we move over to the figure on the right, and now we see better performance, right? And what we can see here is that we're going to have to carefully select the value of IPFR to be below the target, right? Because there might be instances where we're not, and we also don't want to be overly conservative where we're specifying a large value and then we're well within our targets. The different colors denote the different recovery targets, right, for B, C, and D. And with this information, we can then pick appropriate values of IPFR to be below that target, right? So in this case, to meet functional recovery category B goals, we need an IPFR of 1.5. And for C and D, it would suffice to have 1.25 or even 1 for functional recovery category D. Now you're not seeing values for A because A, you might remember, was immediate recovery, and in these provisions we require an explicit evaluation of functional recovery performance for those designs, just because zero hours of recovery or immediate recovery is a pretty ambitious goal. So we want to ensure that has been explicitly verified and not just, it's not just implicit because you're following the design requirements that we're setting out. This seems very simplistic, these figures here. There's a lot happening behind the scenes because in essence, what you see here is the worst performing component of this. What is this? This is effectively, for that one building, the list of all your components, be it structural or non-structural, and then understanding at the different recovery time targets for the different recovery categories, it tells you what is the probability that damage in that component is impeding function. And, looking at this can be overly complex, so it's a lot easier to just look at the worst, right? And then summarize that in a figure for decision making. But it's really useful to understand what are your bad actors, right? What are the components that typically tend to get damaged? And you can even think of this more at a system level, right? So you might be interested more in knowing, are there particular systems that are influencing, these design requirements? And again, what's useful, I didn't necessarily indicate it, but this varies with IPFR, right? So for components that are sensitive to IPFR, you see this color gradient, right? Whereby increasing the IPFR, you reduce that probability. So all of this information is available in the study that I will link to, where you have this type of result for every archetype that we explored. So by doing this exercise for all of the archetypes that we considered, we were then able to come up with recommendations for different functional recovery categories. What's a little bit different here is that we're not specifying an IPFR for a specific system. They're just broadly for different categories, regardless of your choice of system. So we had to think about that a little bit. So in essence, what we did is pick a value of IPFR for different functional recovery categories, then evaluate our reliability performance. And because we sometimes have multiple heights for any given system of choice, we then average those and repeat that exercise across recovery categories to then come up with values that would effectively, meet our requirements across the board with, you might see something that slightly exceeds, 25%, but in general, this was the preferred approach, so we were not be introducing unnecessary conservatism in the design, and this is what led to these IPFR recommendations that we introduced in the standard. So this is a lot of information that I'm providing at a very high level. There are 2 papers that both been accepted. Earthquake Spectre is now transitioning from Sage as a publisher to Wiley, so there's a little bit, I think, of a delay potentially on those, or at least that's how we feel, because they've been accepted but have not yet been made available online. But hopefully they'll come in line very soon. In any case, because they're accepted, what I've done is I've dropped them in a shared Google Drive. So if you're interested, you can use this QR code and look at the accepted version of those manuscripts. There's one that looks at the safety critical structural damage for use in recovery-based design, and then the other one that's all about non-structural components. And circling back, Kristen, you can see, is a primary author, so she did a lot of the heavy lifting on this work. Okay, to wrap up, I just want to share, some high-level remarks and really summarize everything, hopefully, so you can take that message home, if nothing else. And the first one is just recognizing the design philosophy, right? We were asked, this Functional Recovery Task Committee, to develop these provisions, and there was a white canvas, right? This is a new chapter. It's not like we're tweaking existing provisions. We had to start from scratch. And the overall design philosophy, which hopefully you've seen come across this presentation, is that if you're looking at functional recovery performance at the building level, you really need to think about the functional recovery performance of the different systems that you need to ensure that the building level results are positive. And also, for a system to be functional, you really need to worry about the components, right? So you go from this building level analysis to this component level analysis, and we've introduced all these different layers, right, in the development of these provisions. And in fact, it was really useful when going through these code committee meetings to distill things down to the component level, because it's a lot easier to understand how a design intervention changes a component, makes it better, and therefore, makes the overall building level better. And it's a little bit harder to do that if you're just focusing on the building level results. So that's on the design philosophy. In terms of the overall summary of what you'll find in this chapter, I have these 3 key points. So the first one is that we're introducing these functional recovery categories that I've already mentioned that have a specific recovery time target, right? Anywhere from 0 hours for A to 6 months for D. We're evaluating performance at this functional recovery earthquake, which is a risk-based characterization of the hazard, and therefore it has a risk target and a reliability target, and that reliability target is what we're explicitly checking in our design provisions. And the way we're doing this is by introducing new requirements for the structure, primarily RFR and drift limits, new requirements for non-structural systems in the form of seismic qualification of equipment and IPFR. And then I didn't discuss it today, but equally important are other requirements that relate to quality control, right? Because without those, there's no way that all of this comes together. And we even have new roles that we're introducing, like a functional recovery coordinator who's ensuring that there's translation from design to the actual, construction of these buildings. So in a nutshell, this is a high-level summary of what you'll find in this new functional recovery chapter in the provisions when they're released. So where are we? We're in the final stages of this chapter for the 2026 NEHRB provisions. It actually will be published as Appendix A of NEHRB. I mentioned that the NEHRB recommended provisions essentially introduce, novel elements of seismic design that are picked up by ASCE 7. So even though this process is not yet final, we've shared, our latest version of the appendix with the AEC7 seismic subcommittee. I'm involved in this process too, and there's even been a vote at the seismic subcommittee with a lot of comments that are currently being addressed. But our hope is that it will pass at the seismic subcommittee and go to the main committee, in hopes that it will be published also in AEC7 2028. That is TBD. This is happening. This is TBD. And then the ultimate goal is that this will eventually go into the International Building Code. If we can get it into AEC7 2028, then it would also go into IBC 2030. And worth noting is that, this chapter is going in as an appendix, in the sense that it's not going to be mandatory. So the idea is that if you wish to do functional recovery design, now you have a prescriptive procedure to achieve that goal, but it's not... a jurisdiction could mandate it, but it's not going to be automatically mandatory, right, through all new designs. So important to also recognize that. It's very new. There hasn't been anything like this before. So I think it's wise to introduce this in that manner. So that's sort of where we are. If this sounded remotely interesting to you, I'll mention that I'm giving a webinar for SECED at the end of January. And in that webinar, what I'll do is I'll share some of the work of the Resilient Design Coalition, which is a group that was formed on the back of these provisions to try and actually expand that table of structural systems that I alluded to in this presentation, to have many more. Because a lot of the criticism was, you have a very limited number of systems. What about all the other systems? So what we did was we developed a qualification procedure so that any seismic force resisting system can effectively be evaluated for functional recovery design. So that will be the topic of that presentation. If you want to learn more about the Resilient Design Coalition, you can find the website also in the bottom of the slide. And with that, this is just in case the sites are distributed later. I have resources that are more like government level resources, or the ATC 138 report, if you want to look over that. And then I also have papers that my students and I have published that are related to functional recovery. So these are more, for you if you're interested in this topic. And the last thing, just recognize that, this is a group effort, right? This is not just me and my student. There are many people behind the scenes to make this chapter a reality. These are members of the Functional Recovery Task Committee that I was alluding to at the beginning, and in bold are folks that are leading, subcommittees within that overall effort. So recognizing their great contributions. So I leave you with a slide or an image of Vancouver and my email address. I live in one of these tall towers over here. You can see beautiful city surrounded by the ocean and mountains. If you are a PhD student or interested in a PhD or a postdoc, and this sounds like fun work, then feel free to reach out.